So we get to the Z distribution. Now, in order for us to know or to use the Z distribution, at least, we should know the population standard deviation, and in this example, the population mean. Now, most of the time we don't know that. We only know the mean and the standard deviation for our small sample. But imagine we knew that. Then we can use the Z distribution. It's actually easy to explain. Now, I'm going to use an example which is not set in reality at all. It's just to illustrate the point. So, follow along. We have a hormone level and we measure it in the blood. Imagine we always did it by some technique. All the machines that were ever built to do that measurement used the same technique. And every now and then we've got to calibrate that machine. So we'll take a little sample that was made in a factory, and so it doesn't come from anyone's blood, and it has a value of at least exactly 3 in it. So if we were to put it in the machine must measure 3. And so every machine that's ever been made will measure 3 as a mean for that reagent, just to set it that we know the machine works, and we know that it would always give a standard deviation of about 1.44. So imagine we knew this absolutely. That's our whole population. We know that it has a mean of 3 and a standard deviation of 1.44. Now someone invents a new technique, a new method for this machine to work. And we want to know, if we took that reagent that we know has a value of 3 in it, and we added it to these new machines that use the new technique, what was the probability of finding a mean for these new machines from a sample of 25 of more than 3.5, more than 3.5? Now you might say, well, 3.5, it should have given 3. How likely was it that from a sample of 25 we were to find a mean of 3.5 or more? What was the p-value of that? What was the probability of finding that? Now, remember that this 3.5 though, in our sample of 25, is just one of many possible values we could have gotten. We could have taken 25 other machines or repeated this experiment later, and we would get another mean of 3.5 or some other mean. So this one single 3.5 is just somewhere on a curve of many, many possible means. That means we can construct this Z distribution, this curve, and we can ask how many standard errors away from the mean 3.5 would represent. Remember, we said we can't talk about standard deviations anymore. We've got to ask ourselves, how many standard errors away from the mean this 3.5 would be? So first of all, we've got to convert standard deviation. We knew that from the population having been 1.44. We just have to change that into units of standard error. So that is going to be 1.44 divided by the square root of 25, because our sample had 25 in them. And we see we changed that to 0.288. That would now represent 1 standard error away from the mean. 1 standard error away from the mean. Now, we change the question ever so slightly. We just want to know how many standard errors. We know what 1 standard error is now. It's 0.288. How many standard errors away from the mean is 3.5 away from 3? So I've just got to change that difference, which is a half. 3.5 minus 3 is a half. I've got to change that into units of standard deviation. How many standard errors away from the mean is 3.5 away from 3? So that will be a half divided by the standard error, divided by 0.288. And we see between 3 and 3.5 that half a distance is 1.74 standard errors away from the mean. So I've just converted my absolute values. I had a mean of 3 and I had a mean of 3.5. How far is 3.5 away from 5 in units of standard error? That is what we do to try and calculate the statistics. Now we've got to convert that into a p-value. Now that can really be done by a computer does it through numerical calculus, numerical analysis at least of integration. Or many of the textbooks on statistics will have tables at the back, and you can just do that from these tables. And the way that those tables work, you see the Z table there. Down on the side, on the left-hand side, you go down till you find 1.7, and then you go across to the top to find the second decimal, which would be 0.04, so that it would at least in the end read 1.74. You just deconstruct 1.74 by finding the first decimal place, the number in the first decimal place along the left side, and then the top you go to find your second decimal spot, and you look down where they cross and you see, well, that would represent 0.409. So 1.74 standard errors away from the mean, which 3.5 is away from 3, would represent an area of 0.04 under the curve. And if 0.05 was our cutoff value, this is a statistical significant finding. It would only from 3.5 out to positive infinity, remember 3.5 is larger than 3, so we're looking at the positive side, it would only represent an area of 0.04, 4% of the area under the curve. Now, we can use that table in a different way. We could also say what value of standard error would represent an area of 5%, 0.05 under the curve. So we just use that table in reverse. So we actually look at the actual values inside of the table, and we look for something that is close enough, but not to 0.05. Remember, this graph reads from the left to the right. So we're looking from the right out to infinity. So we've actually got to ask ourselves, what is the value of 0.95? Because we want 95%, we want the mark that represents 95%, because we're only interested in the last 5%. And if we read that table off on the left-hand side, you'll find now 0.95, the closest to that is going to be 0.9495 in most of those tables. Of course, the computer will work it out much closer, but it'll be about 1.6, and then you look up, you see it's 0.04, 1.6 plus 0.04 is 1.64. So if we were to go 1.64 standard errors away from the mean towards positive infinity, that little area under the curve there would represent 5% of the area under the curve. So look at this last slide. That is what we have done now. We have the Z distribution, which is a central limit theorem distribution. And 3.5, a sample mean of 3.5, just fell somewhere on that curve. It occurred, if we had to repeat this over and over again, it would occur with a certain frequency. So the frequency we really think about is from 3.5 towards the right-hand side, towards positive infinity. If it was less than, it would be the other side. So you see the little green bar there. You see the 1.64. So for this instance, knowing the population mean of 3, knowing the population standard deviation of 1.44, we know that 1.64 would represent an area under the curve towards the right of 5%. If you are 1.64 standard errors away from the mean towards positive infinity, that would represent 5% of the area under the curve. Finding any value larger than 1.64, expressed in terms of standard error, would represent a statistically significant finding. It would be rare to find that. Now look at it. So we always do from the negative infinity side. That would represent 95% of the area under the curve. We're interested in that last 5%. Now look at the value we found. We converted the difference between 3.5 and 3, that is a half, into units of standard error. So we divided that by the 0.288. That gave us 1.74. So finding a 3.5 was 1.74 standard errors away from the mean. And that fell within that rare area of 5%, of 0.05. That is a significant finding. It would be rare to find that 3.5. It is statistically significant, being less than 0.05 if 0.05 was our cutoff value. But this example beautifully illustrates, I think this last slide beautifully illustrates where the p-value comes from. We construct a graph which is a sampling distribution. We convert the difference into units of standard error, and we see what value would represent areas of 5% and where our difference or our mean or our difference in means actually fell. Did it fall inside of that very rare 5%? Was it rare to find those kind of differences? Or did it fall in an area which was more common to find? Therefore, it really wasn't a significant finding.